formulations of the closed form solutions for shaft, the solution strategy is very different from what we learned before. Okay, and if you remember in the previous chapters, we talk about the average stress function that is based upon stress-based formulation. Okay, if you remember that one, everything we talked about before about stress, average stress function, that is about the stress-based. Now for shaft, and I want to take the different strategy, and that's going to be based upon displacement. Okay, so here, if you like, you can just write a note. And here we from the very beginning, and we're using a different strategy. So hopefully you can compare, think about, and compare the advantage, disadvantage of the two different approaches. Okay, so basically this one is based upon this displacement based. That means we start with the displacement. Okay, and again in average stress function, there we start with stress, different. Okay. So for displacement, again here, look at here. So again here I pick up cross sections. This cross section is at any level here. I simply pick it up, and it doesn't have to be circular. We simply assume it's the general the profile. And again, from in the cross section, I pick arbitrarily a point P. The P representing is a point before the deformation happens. So here, let me use this one to draw this one here. So this is x, y directions. Okay, so before the torsion applied, in that cross section, I simply pick a point P. Then I simply want to study how the point P is displaced. From there, we can get the information about the displacement. So here, from here, I make a mark. So this is the stick. And due to the assumption one, every point in the cross section is undergoing rigid body rotation. That means the length of this stick must be the constant during the rotation. That is based upon our assumption one. Okay. So using this as the center, this as a radius, we mark a point here. So let me exaggerate the displacement to the P prime. Okay. So that means from here to here, P displaced to P prime is along a circular arc. So that is based upon our assumption one. Right? Assumption one on the rigid body rotation. Without assumption one, here would be a little bit harder to start, please. Okay. So in this way, let me say P has the coordinate xy. So again, our goal is to find out the UV. So let me highlight the UV here. So from here, we can see this amount is U. This amount is V. Amount. Here I focus. Here I show it is a magnitude. If you want to justify the displacement for this option, for this illustration, displacement you can tell right away. Okay. So our goal is to find UV. Okay, so in this way we can think how to do this one. This is a very simple geometry here. And P prime, let me say, is x prime, y prime. Okay, so simply UV is this. U equal to x prime minus x, and V equal to y prime minus y. Okay, easy. Now, let me assume this is the angle of rotation, say theta, okay, arbitrary symbol. This is the angle of rotation happened in these cross sections. For example here, so this is our shaft. And let me say the bottom is fixed, okay? So this is the torsion here. So at the top, if you pick a cross section at the top, say this is our angle of rotation, let me call it alpha. So say if you choose a cross section, say this height is Z, and the whole length is L. Then in this way, the angle of rotation here, the theta, you can do the proportional theta with respect to z equal to alpha divided by L. So from here, basically theta equal to z alpha L, right? So basically that is our beta z. Good. Here I have utilized the beta here. So basically here the theta is some number relating to beta there. So keep that in mind. Okay. So again, we're back to here. Okay, so here is a theta, and usually, again, for linear elasticity, we assume the torsion is applied such that everything is in elastic domain. And I say so, that means indicating usually the angle of twist. If we have the calculation, that should be, say, 10 to the minus 3, that kind of the level. Very small. Okay, won't be that huge. It's kind of small angle. Under this situation, you keep in mind theta is a small angle. For small angle, that means we can have approximation. For example, tangent theta is approximately equal to theta, cosine theta approximately equal to 1, and sine theta can be approximately equal to theta. Because of that one, we can make such assumption. We can save this for our use. Okay, now we're back to here. And to utilize this one, let me pick two redundant information to help us. So say the first one, let me call this angle is, again, follow up my lecture notes, please. And my lecture note here, I simply designate it as alpha. Sorry. I'm kind of running out of my, you know what I mean. Okay. For my lecture note here, using its alpha. So basically P, we can, and the radius, so the distance here is simply is radial distance is R. So simply in this way, the X equal to R cosine alpha and Y equal to R sine alpha. So that's additional information to help us. Okay. On the other side, you can see using the polar coordinates, can you see the X prime will be equal to R. Why it is R? Again, because here we do the rigid body rotations, the radial distance constant, right? So that is R. And R times cosine and theta plus alpha. And Y prime is R times sine theta plus alpha, right? Basically, that is this angle, very straightforward in this way. So from here, using this notation, are you able to see U will be equal to X prime minus X will be simply equal to R cosine theta plus alpha minus R cosine alpha. Okay? Then for this case, I can do these things. Then we can expand the cosine into these cosine theta, cosine alpha, minus sine theta, sine alpha, and then remaining R cosine alpha. Okay. And let me implement the things here. So that means let me get the R inside here. Let me R multiply with this one. Let me R multiply with this one. Okay. So I simply distribute R into these terms, and this term basically is our X. This term is our Y. So basically, and again, this one is approximate equal to 1. And this term basically approximate equal to theta. Okay, and this term is X. So from here you can see that is simply equal to minus theta times Y. Good? Okay? And from here you can also, that is Y prime minus Y. Y prime equal to this and Y equal to this, plugging similar process. You should be able to find it, that is theta times X. Okay, so basically the goal is this, equal to minus theta Y and theta X. It's nice. It's very nice. The same, the displacement is a function of the locations. Okay, depends on the point you pick and different location that will kick in here. Also, the displacement is also the function of the angle of the rotation there. And this angle can be related to our twisting to this kind of information here. Okay, that's saying this angle is governed by how big the T is applied, governed by the whole geometry, dimensions, material properties. So basically everything it comes to here. Okay, once we can, it's able to solve for angle of twist, theta can be determined. Once theta is determined, then we are able to determine the displacement. Once displacement is determined, are you able to calculate strain? Right? So the remaining will be very straightforward. How to determine the strain? Epsilon x equal to partial u, partial x. Epsilon y equal to partial v, partial y, right? And then gamma xy equal to 1/2 and partial u, partial y plus partial v, partial x. Okay, so for this example, this will be 0, right? This will be 0, and even for epsilon z, partial w, that one not yet. And so for this one is how much? 1/2 and minus theta plus theta equal to 0, and gamma xz partial w partial x plus partial u partial z equal to 1/2. We don't know the w yet, we keep it. Partial u, partial z basically is this one, is partial theta, partial z times y, right? And you good? So from here you can see u equal to minus theta y. So partial u, partial z equal to partial z and minus theta y. And y is a constant respect to z, so we can get the y out, minus out, so that is partial theta, partial z. What is partial theta, partial z? Here. So that means d theta, dz equal to beta. So from here we can replace this one. Something like this. Good. And gamma yz 1/2 partial w partial y plus partial v partial z. Again, 1 partial w partial y plus partial theta plus v x. Okay, so that's the same. Partial w, partial y plus beta x. Good? Okay. So that should be on the next page here. Here we move this one pretty high. Okay. So that is achieved by, oops. Why here didn't have I made a mistake here, right? David kind of laughed at me. For the definition, the engineering string strength, we don't have 1/2, right? I'm glad you're using pencil. I'm so sorry for other people. You know, the mistake is this. For elastic strain, IJ, we is 1/2 partial UI partial xj plus partial uj partial xi. But for engineering strain, we simply don't have half. It's simply just this one. Right? Sorry, I made a mistake there. Good. Okay. So basically to this point, and that is what we've been showing on this slide. Okay. So here in this formulation, the same thing like we formulated here. And before we move on, and let me summarize the result here for everyone, and that's almost 4 lectures a day. So again, here is the cross section, and right now we start from our displacement formulation of the displacement. Okay, so this is xy coordinate. And there we're starting from to track the displacement of a point P, and that has a coordinate xy. And this cross section has the normal to the z direction, we call the z plane. And sorry, I need to change that word. In my lecture note, I use x plane. I use xy plane. I don't know what I was thinking. I use xy plane to indicate this xy cross section. But here, let me change it. Okay, let me change it. This cross section has the normal to z direction, so that's supposed to be z plane. Okay, this is z plane there. We look at those information here. We know the corresponding, all the strain elements are 0 except this one. So that means you can see if we multiply this with g, that becomes tau xz. What is tau xz? This one, let me plot this one onto this plane. So in magnitude, this one is tau zx. That is the strain stress in z plane pointing to x direction. At the point P here, so that component is strain strength is zx, like this one. Good? The second one, again, in magnitude equal to that one, multiplied with g. That gives us the tau z in z plane pointing to y direction. So right now, actually, we have obtained is the two stress components. If you want to visualize in a vector, because this one has been applied into the z plane, so that basically we can visualize as a vector, something like this one. For example, if you calculated the tau zx is say minus 100, in this way, when you draw it, you need to flip the direction, right? If you calculate tau zy is minus 100, and then again, flip that term, flip the direction in terms of sign convection. From this point onward, before we take in more information, if I will ask you what is the magnitude of the strain stress, then it simply is this. In terms of this drawing, this one, right? That is the magnitude, tau. How to calculate? Simply is tau zx squared plus tau zy squared, right? If you still remember our previous test, one question exactly is about this one, right? Okay. So I will take a break here, so we're done here.